In order to solve a linear system, we are going to perform operations on the equations in order to change them, but not change the solution set. And we'd like to obtain a linear system that has the same solution set, but which has an augmented matrix that's in row echelon form. And this way we will be able to easily recover the solution set as shown in the previous video. Now, what are the type of operations I can perform on a linear system that will not affect the solution set? There are three of them, and they're listed on the left here. And to each of them corresponds a row operation that I can perform on the augmented matrix that is associated to that linear system. Operation number one is to multiply an equation through by a non-zero constant. Now, what do we mean by this? In order to explain all these row operations, I have included a little example here. Here's the linear system that you see at the bottom right there. And I have numbered the equations 1, 2, and 3. And what I could do is multiply equation 1 through by 3, and it will not change the solution set. And what would that give? If I multiply equation 1 by 3, I would instead have 2 times 3, 6x plus 3y minus 9z is equal to 15. Now that's not changing the solution set because these two equations, they're the same plane. So essentially, if you think of this linear system as three planes intersecting, where they intersect is still the same because by multiplying equation 1 by 3 through, I have not changed what this plane looks like. So it's still the same plane, so it intersects the other two exactly the same way. Equivalently, if I work with the augmented matrix, I could multiply equation row 1 by 3, and that would be the exact same thing as multiplying the equation through by 3. So the corresponding augmented matrix would now look like this and would still have the same solution set. Operation number 2 is just interchanging two equations, right? So that's just interchanging the order in which the equations are shown or in which the planes are listed. Of course, that's not going to change where they intersect or the solution set. So for example, I could say I'm going to switch 1 with 3, and I would essentially have y minus 3z equals 4, x minus y plus z equals 2, and 2x plus y minus 3z equals 5. You'll agree that it's the same set of equation, really. You know, it's just ordered differently, so it has the exact same solution set. In terms of the augmented matrix, I could say I'm going to do row 1, row 3 like this. This is a symbol that I use, and it would just copy the third row here, copy the first row there, and not change the second row. And that's interchanging the two rows. Finally, there's adding a constant multiple of an equation to another equation. Maybe that's the hardest one that it's the hardest operation. Let me rephrase this. It's the most difficult operation to that we believe will not change the solution set. I don't think that was better, but what I mean is it's hard to believe. Okay, here we go. It's hard to believe that this type of row operation will not change the solution set. Okay, that's what I meant here. It's said simply. What kind of operation is that? Well, for example, I could here's what I could an example where I'd want to use an operation of this type. Suppose I'd like to eliminate the y here. So what I could do is simply, I could add to equation 3. Actually, let's make this slightly different. Maybe let's say there's a little 2 there. Okay, just changing it. Okay, I'll change it here too. Okay, let's say I want to eliminate the y there. What I could do is say I'll take equation 3 and I will add half of equation 2. Okay, what is that going to give me? Well, equation 1 won't change. Equation 2 won't change. But equation 3 will change a bit. If I add half of equation 2, we'll get half of x. But look, I won't have the y anymore. Y plus a half of minus 2y, that's y minus y, that's 0y. And minus 3 plus z plus a half of z, that's what, minus 9, 6 half plus 1 half minus 5 half of z is equal to, oh, that's hard, 4 plus 1, 5. All right, okay, I don't have the z anymore here. Okay, so I've eliminated the z. In terms of my augmented matrix, I would write row 3. I'm going to add a half of row 2. And then instead I would have the following coefficients. So row 1 doesn't change, row 2 doesn't change, but row 3 changes to 1 half, 0, minus 5 half, and 5, like that. Now that's changing the planes though, like this plane and that, so this plane here and that plane here are not the same. So we may think, oh, that's going to change the way those planes, the 3 planes intersect, but no, it's not changing where they intersect. In fact, the solution set isn't changing, and the reason for this is that I can always go back to the original linear system by, let's say, subtracting half of equation 2. And here I could go back by subtracting 1 half of row 2 to row 3, and I would be able to go back to the original linear system that I have. So this one's not changing the solution set either. So we're going to be applying those types of operations in order to put our augmented matrix into row echelon form. So I'm going to go through the steps of our method, our algorithm, our recipe that's going to put the augmented matrix into row echelon form. So here's the, I've chosen to do the example that's in the book. So it's the example on page 14. So you can either read it or you can stay with me and go through the steps together with me. Okay. So this is the linear system that you have on the left, and I've written down the augmented matrix of that linear system. So we are going to work only with that augmented matrix. Now, step 1. So I won't write everything down. So I'm going to read it, and if you want, you can look at what's written in the book. Okay, it's the same. I'm just going to read out what's there. So there's step 1. Step 1, we're going to locate the leftmost column that does not consist entirely of zeros. So leftmost, right, means going this way, and we locate the column that does not consist entirely of zeros. So it's the first column, right? There's some 2's there. Okay. So this is step 1. That's it. Step 2, interchange the top row with another row if necessary to bring a non-zero entry to the top of the column found in step 1. So what's the top of that column? It's this entry here. What we want to do is we want to make this into a 1. And eventually that's what we want to do. And the way we're going to do this is we're going to multiply the equation or the row throughout by a non-zero constant. But because it's 0, it's not going to be possible if I don't apply operation 2, which means interchange 2 equations. My goal is to get a non-zero up there, and after that I'll make it into a 1 by multiplying the row throughout by a non-zero constant. So right now I identify I have a 0, I don't want it there. So I essentially you pick a row. Usually you pick the next row available that has a non-zero there. So what we will do is we will interchange these two. Okay, so the way we write this down is I put R1 arrow row 2 and I will just interchange the rows. So we've done step 2. Now our goal is to bring a leading 1 here. Remember, I want in my Gaussian form that the first non-zero entry wanted to be a leading 1. How do I do this? I'm going to perform a row operation of type 1. I'm going to multiply it throughout by a non-zero constant. So row 1, I'm going to multiply it by a half. This way, everything is divided by 2, but my first entry now is going to be 1. 6, 14, like this. Okay, now having done so, what are we going to do now? So you'll remember that I've got a leading 1 here, and I'd like the leading ones to appear diagonally like this. Okay, so which means that below here I need to have lots of zeros. Okay, so then my next step, what I'm going to do is below the leading 1, I'm going to start introducing zeros using row operations. So what I want to do is put zeros below the leading 1. That's the first thing I'm going to want to do. Now I'm kind of lucky because I already have a 0 in the second row. So all I need to do is introduce or replace that 2 at the bottom by a 0. How do I do that? I'm going to do operation number 3. So we are going to take row 3. And to introduce a 0, we're going to be subtracting a multiple of the row that has a leading 1 in that column. So what's the row with the leading 1? It's row 1, right? That's the leading 1 right there. So I'm going to be subtracting 2 times row 1. So it's very easy to figure out what number to put here. It's the exact same number you have there. So by doing this, we're not going to change row 1 and row 2. So we're just going to recopy them. And now we're going to perform the row operation. So we do, to get this entry here, we have to do what? 2 minus 2 times 1. So of course that's 0. That's the whole purpose of this row operation, 0 there. 4, now we're dealing with this guy. 4 minus 2 times 2, that's 0 again. Minus 5, minus 2 times minus 5, so that's minus 5 plus 10, so that's 5. And I keep on going, and I'm going to get the following numbers. Okay. Once we have introduced a leading 1 up there, zeros below it, okay? What we do is we will cover that row. We'll omit it for now. And we're going to reapply everything we've done so far with the remaining rows. So we consider this what's called a submatrix here, and we reapply those steps that we just did. So what are those steps? Well, identify in the submatrix the leftmost non-zero column. So it's not this one, it's not the first one, not the first one, it's this one. Okay, remember I'm just working with the last 2 rows now. Here, I would like this to be a leading 1. Okay, how do I do that? Well, and you need to make sure it's a non-zero. It is. Okay, that was step 2. Step 3, I will divide that second row by minus a half to introduce a leading 1. So I divide by I multiply by minus a half or divide by minus 2, row 2. In order to introduce a leading 1. So see this entry now is going to be a 1. So of course the first row isn't changing. So there's a lot of recopying, right, in applying this method. And we divide everything by minus 2. So minus 7/2 and minus 6 here. And then we just recopy the third row. It's not changing. Okay, it's important to realize as we do this, our planes are changing, but we're not changing where they intersect. After that, what do we want? We want to, this is step 4, we want to add a multiple of row 2, the one that includes a leading 1, right? Our leading 1's here. Add a multiple of row 2 in order to replace that 5 by a 0. How do I do this? It's like I said, it's very simple. You take row 3 and you subtract what? How much times row 2? Well, 5 times row 2. How many times? Row 2, 5 times. So, and I just recopy row 1, row 2, and here, of course, now I'm going to have a 0 here. That's the whole point. I keep going, and here's the third row now. By the way, why am I working with the always the row with the leading 1? Say I'd be working with row 1 instead of row 2. So I'd be doing instead here I do row 3 minus maybe plus row 1. That sounds like a good idea because that's going to make this a 0 again, right? 5 minus 5 and 5. But what's going to happen is that these guys here will not remain 0. See, in fact, they will become 1 and 2, and I will have destroyed those zeros that I need desperately there, because remember, I want my leading 1s to sort of appear diagonally, and below them I want 0. So if I'm putting non-zeros there below, I'm going to destroy that structure, so I don't want that. Okay, so this would be a bad idea. Row 3 plus row 1, I would not make progress there. I actually undo my good work. Okay, so now I've got in this column 1 and 0, exactly like I wanted. So what do? Well, I'm going to now cover up. I already had covered up the first row. I'm going to cover up now the second row because I'm done with it. And I'm going to repeat my work with the remaining submatrix. Now the remaining submatrix is just the third row, this row here. Okay. So what do I want to do now? Well, I want to apply those steps again. Identify the leftmost non-zero row. In this case, we're just working with one entry. Here it is, leftmost non-zero. What do I need to do? I want to make it a leading 1. So I'm going to multiply row 3 by 2. Recopy everything again. Okay, and multiplying everything by 2 will give me 1 here and 2 there. Okay, and I don't have zeros, okay, to put below this one, so I'm kind of done. Okay, so now I'm done with my recipe. I have, if you look, my matrix in row echelon form. Look at the leading 1s. They appear diagonally. Below them, you have a whole bunch of zeros. Right? Where are they? Here they are. All the zeros below those leading 1s. Okay. Well, below the diagonal, in the second column, I don't have zeros below a leading 1, but right? But you want to have zeros there. Okay. And what else? Oh, the other thing is, if there would be a row of 0, I would like it to be at the bottom. Okay. So that those steps, they will ensure that too. So we don't have this occurring in this example. So we now have our matrix in row echelon form, and it will now be a lot easier to recover the solution set using what's called a backward substitution. So we'll start with the last equation. Remember, each row is associated to an equation, and we will move our way up, solving the equation each time for our leading variables. What are the leading variables? Those are the variables where you've got a leading 1. So those are called leading variables. You'll see why they are important. So maybe to explain how we do our backward substitution, let me rewrite the equations associated to this linear system. Here we go. So now you see each equation starts with a leading variable. Okay. And looking at the last equation, you see I can easily figure out what x5 is. It's 2. So we'll move upwards like this. I start with the last equation, which just says x5 is 2. After that, I move with the second equation. x3 is what? Well, it's minus 6 plus 7/2 x5. And now I know what x5 is. I can replace x5 by its value, which is 2. So that's going to be minus 6 plus 7, which is 1. So now I know x3 is 1. And finally, x1, actually I need a lot of space, so let me write x1 here. Solving the first equation for x1 gives me x1 is 14 minus 2x2 minus 5 plus 5x3, right? Remember the sign's changing as you send it on the other side of the equality sign, plus 6x5 like that. And now I can replace the values of x3 and x5 in there, right? So x3 is 1, so 5 times 1. x5 is 6 times 2. What about x2 and x4? Well, x2 and x4, right? They could be anything, really, okay? They could be any value, and all these equations would be satisfied. So we will, normally at the beginning of our solution, we will assign arbitrary values to those variables. We'll say S2 is S, and S4 is T, where S and T are any real number. So you see, if I replace x2 by 1 and x4 by root of 6, I'm going to get a value for x1 that's valid, that will satisfy the system. And I can do this, right? Change the value. Maybe choose root of 7 here and 1.2 here, and still works. So that's why any arbitrary value will actually work. So I will say that those values are S. Let me write a nice S, S, and x4 is T. So the way it works is that you start your backwards substitution by assigning parameters to your, which means arbitrary values to your free variables. So for the free variables are the ones that are non-leading. So you've got the leading variables here, and you've got what are called the free variables. Okay, and those are assigned parameters. Any parameter is, in this case, it's an arbitrary value that you assign to each of your free variable. So once you solve for x1, you get what? You get, well, simplify. I mean, here you get 14 minus 2s plus 5 minus 3t minus 12. And let me group that together. 14 plus 5 is 19 minus 12, 7 minus 2s minus 3t. So we're kind of done now, so we're going to regroup everything together. So the solution set, and I want you to write that on an exam, okay? Please don't leave me figuring out where x1, x2, and x3 are. Okay, you group them all together. x1, x2, x3, x4, and x5 is going to be equal. So x1 is what? It's 7 minus 2s minus 3t. x2, sorry, is s. x3 is 1. x4 is t, and x5 is 2. Okay, and if you want, you can put st, part of the real numbers, but you don't have to. It's understood. It's this way. Okay. And sometimes, okay, you'll be asked to find a geometrical interpretation or description of your solution set. Okay, what's the geometrical interpretation here? Well, let's take a look at this. You can do it by writing your solution set, which is in vector form, and you can do that by splitting it up into the constant part. So what are the constants? 7, 0, 1, 0, 2. So those are the constant part of each variable. Actually, I'm highlighting S, but it's S is S. Is there? Well, S is 0 plus S, right? So there's a 0 there that I'm considering, and then 1, and then there's 0 plus t, so that's the constant part in x4. So this is where my second 0 comes from, and then 2. So 7, 0, 1, 0, 2. And then what? And then plus, I'm going to run out of space here, plus s times, and let's look at the coefficients of s. There's minus 2, 1, and then 0, 0, 0. And plus t times minus 3, 0, 0, 1, 0. So if you add this up, you get back what you had above, what we have above. And what is this like? This is like a point plus a multiple of a first vector plus a multiple of a second vector. Hey, that's a plane, remember? So if I've got a plane, okay, with a point P0 with two vectors in that plane, right? Any point on the plane can be obtained by, if I want to point here, right, starting at the origin, I can reach that plane by going first to P0. So that's the first, that's OP0 right there. And then you take a linear combination of V1 and V2, which allows you to move anywhere in that plane. So by taking a linear combination of V1 and V2, which is this, you can reach any point that's in that plane from point P0. So this is our geometrical interpretation. It's a plane that passes through P0, which is 7, 0, 1, 0, 2, and containing the vectors V1, let's say is minus 2, 1, 0, 0, 0, and V2, which is the second one, which is minus 3, 0, 0, 1, 0, like that. So that's what a geometrical interpretation is. Okay, you have to describe, is it a plane, a line, or a single point.